We had a very lively and I think very productive morning session of this conference. And now it's going to continue at least as interesting as we had it, because you're coming to what I think is an important session on changing climate events. And you didn't have to watch the news very often this year to have seen the effects of extreme weather events and extreme climate events all over the world, be it in the US or in China or closer to home in northern Italy or close to where I live in Germany, in the western part of Germany. So it's extremely timely that we have three world experts talking about different aspects of changing climate events. And I'm very happy to be able to chair this session. So we will start with Anthony Davison from the EPFL, École Polytechnique Fédérale de Lausanne, who will talk about statistical uncertainty and extreme climate events. I'll give you a warning 5 minutes before.
Thank you very much for the kind introduction. I'm delighted to be here. It's the first academic trip for 18 months, and it's such a beautiful place in such a wonderful setting. I have to confess, I have imposter syndrome, but I have it correctly because I'm actually an imposter here. I'm a statistician rather than a climatologist. I'm a statistician who works on the development of methods, mostly for modeling extreme events, not specifically extreme climate ones. So I feel somewhat nervous and a bit out of place. The work I'm going to talk about is, so I'm going to talk a little bit about statistical uncertainties to start with, and then I'm going to talk a little bit about the methods we use. Hopefully those will be for modeling extreme events. And then I'm going to give a kind of very quick sketch of how to model a particular type of event using, in quotes, the latest technology. The work I'm going to describe has been done jointly with a large number of former PhDs, postdocs, colleagues, and so on, and some acknowledgements are here. So let's start off with one of the early members of the Accademia dei Lincei, Galileo Galilei, who was asked, he wanted first of all to study medicine, but accidentally walked into a mathematics lecture and decided he really wanted to study mathematics. And there's this famous quote in his book, Il Saggiatore, the Book of the Universe. I won't attempt to do the Italian, though I suppose that would provide some light relief for you. The Book of the Universe cannot be understood unless one first learns to comprehend the language and the alphabet, and then he talks about the use of mathematics, and in particular about geometric objects. And he finishes off, without understanding this, one wanders around in a dark labyrinth. He'd obviously been to Trastevere by night, I think. Nowadays, I think he would probably say, I have to understand probability and statistics in order to understand the universe. Of course, as well as geometry and physics and so on and so forth. And probability has two main functions in scientific discourse, it seems to me. One of them is just the description of variation, how we describe the variability that we see around us in natural phenomena, sometimes called aleatory uncertainty. And the second main function is the expression of uncertainty, what one might think of as epistemic uncertainty of our knowledge. And those two are rather different. One of them is describing, if you like, repeated events in natural phenomena. Maybe they're not exactly repeated, but we can think of them as being quasi-repetitions. And the other is about our state of uncertainty. And we already had a number of expressions of our uncertainty this morning with Andrew speaking about 90% sure of something and so on. A very incomplete history is here. There's a certain theme here. Girolamo Cardano was an Italian who wrote the first book on games of chance. He wrote it in about the mid-16th century. It wasn't published for 100 years until after his death. Jacob Bernoulli managed to publish his very important work only 5 years after his death. Thomas Bayes managed to publish his famous theorem only 2 years after his death. He actually died in 1761. And the subsequent people down here, Laplace, Kolmogorov, Finetti, Jeffreys, and so on, managed to publish within their lifetimes. It's good to think that probably in the future, people who have yet to be born will be publishing before they're actually born, if this trend continues. Why are they here? Well, there are basically 3 thoughts about how one should express uncertainty can be found here. Laplace and Bayes and Harold Jeffreys thought about it in terms of, we observe some facts, we want to then say something about the state of the universe, and we can do this in an objective way. And this has come to be known as objective Bayesian inference. It relies on some sort of objective statement of what we know in advance of then observing the facts and transmuting that into posterior inference. De Finetti, another member of the Academy, said famously that probability does not exist. And by that, what he meant was that objective probability doesn't exist. I can have my view of uncertainty, Bruno can have his, and so on. We all have different views, and they don't have to coincide. And of course, this is not a very useful way of talking if one wants to convince politicians that about facts about the universe about which we're pretty sure. Fisher and Kolmogorov took a different view, which was that not Bayesian, but we think of the uncertainty as coming from repetitions of the universe, sampling, and that leads to what's sometimes called the calibration of uncertainty. And what the idea there is, if we state something and we're 90% sure of something, if it were to be repeated 100 times, 90 times it would be within our uncertainty expression. And this idea of calibration is, of course, crucial also in the other forms of uncertainty, because we wouldn't really trust an expert who was persistently wrong when they thought they were saying something. Sources of uncertainty, of course, are many, and I don't really need to go through them here. There's problems with the data, there's problems with our understanding. In the context of climate science, there can be problems of computation, the level of discretization we're able to achieve in order to model, to get sufficient resolution for climate modeling. And then, of course, in statistical modeling, there are many other sources of uncertainty that come in. The problems with estimating underlying processes, problems of predicting them, even if we could estimate them well, getting the wrong statistical model, and then maybe framing error, which one might think of as being answering the wrong question. Apart from just pure modeling, when we come down to thinking about impacts, we also need to think about the levels of the components of risk, hazards, exposures to hazards, vulnerabilities as a result of those exposures. And it was a relief, I must say, when I came into the building to notice that we're not really very vulnerable at least on the second floor, to flooding from the Tiber. Only on the ground floor, the highest, I think it's about here, is the highest flood so far, so we're probably quite safe this afternoon, I believe. But potentially, those vulnerabilities and uncertainties about them may, of course, be crucial in thinking about impacts of climate events on the individuals. And then, of course, the effects of possible mitigation actions. We heard a little about that this morning, the idea of geoengineering and what the consequences that could have, unintended, of course, as well as intended ones. And I just wanted to echo something that was mentioned this morning. Clearly, we have to put our money somewhere, and maybe thinking about things in terms of decision theory, of course, not in the numerical way, purely numerical way that would be used one finds in textbooks, but maybe that would help to choose the improvements that would most reduce the overall uncertainty in this list here, and I'm sure that you can all think of other sources of uncertainty that feed into climate science. Pardon me, I'm losing my voice already. So why model extremes? Of course, one reason is just to try and estimate what changes in extremes could occur, either to understand them or to do more or less detailed forecasting of what the future holds. A second reason is, and of course related, is risk assessment at a single important site. A few years ago, I was involved in trying to do risk assessment for the Swiss nuclear installations, and there the ones interested really strictly in what goes on at Mühleberg or Gösgen or Betznau and so on. Those are the crucial things. That's what's most important. But in other settings, one might want to think about events, the risk of crop failure over a large region, the insurance payout following a major windstorm, and so on and so forth. And something that's become a very big industry over the last 15 years or so is the attribution of specific events to possible causes. Is some event, wildfires in California, due to climatic change or heavy flooding in Germany? And there's now a consortium that produces attributions where they can very rapidly after such events, saying this was or is more likely or maybe is not more likely due to the effects of the warming Earth. All of these things above will involve some form of space-time interpolation or extrapolation. Even risk assessment at a single site will typically involve bringing in information from around that site, if only because usually the data at the particular site are not very extensive. In order to do a spatial or space-time risk assessment, one is also going to need to do good marginal modeling, but also good joint modeling of the different extreme events. And very often the risk estimation will involve what I think of as bold extrapolation, not just minor extrapolation. In the case of the nuclear power stations, the legal requirement is to think about events that have got a 10 to the minus 4 probability in a single year, but one's going to try and do this based on 30 or so, maybe 35 years of data at that place. And of course, that's a wild extrapolation. On the other hand, it's a legal requirement, so somebody, and one hopes somebody sensible, should be trying to do this. And the basic problem we're all obviously conscious of, the events used to be at least rare, their probabilities are small, and the data that may be directly relevant are typically going to be limited and possibly quite unreliable. So why do we need specialized models and methods? Geostatistics, of course, is an extremely well-developed domain of statistics, and it's a standard use for modeling spatial data of various different sorts, gridded, point data, and so on and so forth. It's mostly based on multivariate normal distributions, Gaussian processes, and such like, and those are inappropriate for rare event modeling. And they're inappropriate for rare event modeling because the tails of the Gaussian distribution are just too light to be able to accurately capture most tail behavior. They cut off, essentially, we tell students in basic courses, if you see a standard Gaussian variable outside plus or minus 3, it probably isn't, it's probably an outlier, because that's a very unlikely event, but that would not be at all unlikely in the context of extremes. A second problem is that typically extrapolation from a fit to the entire distribution can be misleading because different fits to the bulk can give you very different tail estimates. And this problem is even worse for multivariate data, for which the Gaussian models, these geostatistical models, will actually predict independence of very rare events. This is sometimes called the formula that killed Wall Street, because the Gaussian copula, which summarizes this dependence, was widely used in the financial industry leading up to the crash of 2008, and essentially led to a total misestimation of the risk of many very bad things happening simultaneously. So just to rub that point home, what I'm showing here is, what I'm showing here is two different distributions, the bivariate distributions as you see. They have the same marginal distribution, and what you see here is on the lower axis here is the joint probability, the conditional probability of a big event on the vertical axis conditional on the correspondingly large event on the horizontal axis. So if you like, it's the ratio of this area here, this top right square at the top right hand, to the total area here, or the total probability in that area. And you see that in this case here, the probability is converging towards a constant 0.8, and in this case here, the probability is converging to 0. The left one is the bivariate Gaussian distribution with quite a high correlation, 0.9, and the right-hand one is an extreme value distribution, and that there you can see that there's quite different joint tail behavior of these two things. And this leads, in the context of spatial prop modeling, to quite different behavior between what's called asymptotic independence, which corresponds to the Gaussian process, and asymptotic dependence, which would correspond to an extreme value process. And the one way to think, so here we've got some more images. Here you see total independence. Here you see an asymptotic dependent process in the bottom left, where you can see, of course, it's totally unrealistic as a model for a climate process, but it illustrates the point I'm trying to make. And then over here in the other panels, you see a variety of different sorts of process that can be used, in this particular case, could be used to model maximal rainfall per year in the region of Zurich. And the basic difference between these two different types of process is an asymptotic dependent one behaves roughly like this as it gets high. So a big event here occurs at the same time as a big event here. Asymptotic independence tends to become peakier as it gets higher, so individual events tend to occur separately. And of course, whether which of those is going to be appropriate will depend upon the phenomenon you're modeling. Typically, one finds that rainfall exhibit asymptotic independence, whereas, for example, heat waves appear to mostly demonstrate asymptotic dependence. Okay. Now what I want to do is just to talk very briefly about the classical methods, and then at the very end, I'll come back and talk about a more general setup that I hope will demonstrate the sort of things that are possible. So I'll talk briefly about the Vargas Tragedy. This was an event in the Venezuelan coastal state of Vargas at the end of 1999. You can see here some idea of the terrain, massive hills. There was around 70 centimeters of rain over the 3 days, the 14th to 16th of December. Then there were large mudslides, debris flows and such like. And basically this little town here was wiped out. Nobody knows how many people died, probably 30,000 or so. But this was a massive loss of life. Okay. The available data up to the time looked like this. There were annual maxima from not far away, and then daily data that looked like this series from roughly 1960 to the year 2000, 40 years or so. And then the event was this. So here you can't see, but there are 3 or 4 very large events here, and the total, the largest, the middle day was about 400 millimeters of rain, 40 centimeters. The total over the days was around 700 mil. Okay? And one of the points I wanted to make here, just looking at this picture, is that a statistical analysis now that's performed immediately after this event, as if one was to do an attribution study on this, would clearly overestimate the probability one would clearly estimate the probability of such an event as being too high if we do the analysis just after the event and don't take into account that we've done it just after an event. Whereas, of course, if we do it without the final observation, we're going to get the probability too low. So one needs a proper statistical analysis here that does the estimation, assuming with the correct assumptions, and for that you have to somehow formulate a stopping rule to say, well, this is why I would have stopped the analysis, and then take that into account when one does the analysis. And there are ways to do that. Extreme value analysis statistics here needs a basis for extrapolation outside the sample. And there's 2 basic approaches here. One is to model the block maxima with the generalized extreme value distribution. Basically, that involves replacing all the data here by the red points, and then and of course somehow taking the fact that this is there's a stopping rule being applied for the last one. Okay, so we're going to fit a particular distribution to those ones. The other possibility is to impose a threshold and model the points, the exceedances over the threshold here using the generalized Pareto distribution. And that's what I want to focus on, a generalization of that in the last part of this talk. Okay, so we fit a particular distribution to these exceedances and use that to try and model the extreme events. Okay, the generalized Pareto is a flexible distribution. Some example density functions are shown here. It can be uniform, it can be triangular, it can be exponential, and it also may or may not have an upper bound. And the shape parameter, this parameter xi that is mentioned in the caption here, is the thing that determines the tail behavior. The importance of these two distributions is that they both allow extrapolation to rare events in a general and mathematically justifiable way. Of course, whether the mathematically justifiable is necessarily appropriate in the real world is another matter. But these, one would, of course, need to do assessments of fit to be sure about that. But at least this gives a general framework within which to apply, do some statistics. They both depend upon this shape parameter, and this shape parameter has characteristic ranges for different types of data. For rainfall, there's folklore that it's typically around 0.1, which means no upper bound. For extreme hot or cold temperatures, typically it's negative, which means such values are bounded above or below. But of course, the bound may not be very far away, or it may be a long way off. And for high winds, typically the shape parameter is somewhat negative. And it's hard to estimate, and its uncertainty dominates extrapolation, so one needs to somehow think about combining data using Bayesian methods or regularization or something when one tries to estimate it. And I won't go into them, but there are very many associated methods and refinements for use in applications. These are very widely used technologies in a whole wide variety of environmental sciences, and I'm sure that many of you and your groups have used them in different ways. Let me now change focus and talk a little bit about European windstorms for the last few moments of my time. Here are two examples. Daria, in the beginning of the 1990s, struck mostly the UK and led to 97 deaths, about $8.2 billion of damage, equivalent to a Category 1 hurricane. Lothar, about a decade later, led to a similar number of deaths, similar amounts of damage, but struck more Central Europe. Close to where I live in Switzerland, the highest wind speed was about 56 meters per second, which is, as you know, appreciable. And of course, we expect future windstorms probably to be of this general size, to be more probable and more destructive. More destructive probably because they're going to be more energetic, but also perhaps because we are more exposed to them. These are complex space-time events, and what I want to do now is just to explain how one can go about modeling them using recent extreme value technology. Not because of this particular class of events, but to give you some idea of the sort of things that can be done. Okay? So the sort of data that are available look like this. These are, for Storm Daria, every 3 hours, the maximum wind speed sustained over at least three seconds, and these are from the ERA interim reanalysis. So this is a data product. And what we have is data like this for every 3 hours over a long period, and what we would like to do is to pick out the destructive windstorms. And the basic approach is the following. We're going to define something we call a risk functional, which is designed to pick out some aspect of the type of event we're interested in. We're going to choose the events for which that risk functional exceeds a threshold, exactly as we would do with the generalized Pareto modeling. But then instead of just taking the observation, we take the entire event surrounding that observation, if you like. And then we aim to compute the probability that our process lies in some rare event set, A, conditional on the risk having been high. And then, of course, we need to model also the probability that the risk will be high. And we can do that, this last part, as a function of prior conditions, explanatory variables, and climate variables, and such like. And then we use the model of the large event, this quantity here, the X as ST, using something called the generalized Pareto process, which is basically something like a Gaussian process, but which has generalized Pareto marginal distributions everywhere. And we can construct that in a flexible way based, for example, on the classical space-time geostatistical models. We'd use the usual things to check fit, and then we can use simulation to estimate the rare event probabilities. So let me just go in a little bit more detail on these things. For the risk functional, in this particular case, what we've chosen to do is to focus on this green region. It looks rather blue to me, but maybe that's just the light. This region here, which contains some major European cities, and where one might imagine it would be the risk to infrastructure, the loss if a major event struck those points, could be extreme. The X of S and T represents the wind field at location S and time T, and what we want to do is to choose those particular events with high values of the spatial average of the wind field integrated over this region here. Okay, so we're taking the average over this green or blue region, depending on what you're seeing. And here's what we see. We're looking at winter storms. Here are the winters from 1979 to 214. We have a time series corresponding to the value of the risk functional. We look at the largest values of that functional. Those are the red dots here. And then we pick those off as being the events we're interested in. Okay, and so each of the events will consist of a series of maps like the map we saw for Daria. Okay. What we see also on this picture is some lines that show storms from a different catalogue, and the idea here is to show you that the two more or less agree, but because we're dealing with risk in a particular place, they don't agree exactly. It could be that certain storms from that catalogue strike elsewhere and are not actually damaging in terms of the risk functional. We think in terms of, so this is just to model the event probability. The top line shows the probabilities of observing extreme storms in the given winters. Below that, you see the modeled probabilities, and those probabilities depend upon the value of the North Atlantic Oscillation and the value of a particular temperature anomaly. And you can, of course, bung in lots and lots of different quantities to use for the modeling there, whatever you think is useful in terms of the climate modeling. Here are some example generalized Pareto processes. These are just spatial processes, and here you can see with different covariance functions the sort of processes one can generate. One can use a wide variety of different covariance functions, both in space and in space-time. And what I'm going to show you now, the results I'll show you at the end, were generated using a space-time covariance process that's designed to model windstorms in a more or less appropriate way. Here you can see some assessment of the fit of the model. If the model fitted perfectly, all these red points would lie along the diagonal gray line, and you see that, of course, it doesn't fit perfectly, but it doesn't do a terrible job overall. These lower six panels correspond to what's going on at these 6 green points in the map above, and the top panel here corresponds to the risk functional, which, as you see, is modeled reasonably well by the process. And then here's a simulated storm generated using our model. And of course, one can just keep on generating them and estimate risks of particular extreme events. And you see this is the development over time, analogous to what we saw with the Daria plots before. Okay. Unfortunately, we had to leave out Switzerland and south of the Alpine areas because the resolution for the interim analysis isn't really good enough. Okay, so just 7 last words. Extreme value analysis, extreme value modeling, of course, has got lots of applications in climate science and has developed very greatly in recent times. There's been an awful amount of effort in developing complex modeling, in trying to think what, in interacting with climate scientists, environmental scientists, and so on, and in thinking about how to import this useful mathematical work and more generally for scientific knowledge, for building technological advances and so on. There's a large community of mostly young scientists. I'm one of the old guys, and they're very eager to collaborate with people. And as I hope I've shown you, the area now offers much more than just the classical approaches, the generalized extreme value, generalized Pareto distributions. In brackets, I just wanted to underline again, one should try and take into account these stopping rules when doing analyses immediately after big events. It's not easy to do so because the stopping rules are somehow implicit, but at least one has to think about it. There's journals, of course, devoted to the area. There's a conference. And if you were interested by any chance in the generalized Pareto work, you can find it on the archive. It's joint work with Raphael de Fondeville. Thank you very much for your attention.
Thank you very much, Dr. Davison, for an excellent talk and introduction to a very important topic. I am sure there are questions. Because statistics is pretty important, especially if you want to look at extreme weather and climate events.
Ready to be connected from far away.
Okay.
Okay, I'm going to speak. I don't know if you called me or somebody else just now, but if it was me, let me speak. I had a question. Can you hear me?
Yes, we do.
You can? Okay, great. So I had a question about attribution, and I realized, you know, you're not a climate expert, and I'm kind of taking advantage of that because you probably come at this with a neutral perspective. The thing about climate attribution is that, and we've seen this, as you say, rapid response media, I mean, they're very high profile now in the media, that climate change has increased the probability of some event by some number, 20%, you know, 60%, whatever it is. And these are done by running models, climate models, first of all, you know, without increases in carbon dioxide, and you try to count the number of extreme events of the type you're interested in, and then you run the models again with the increasing levels of carbon dioxide, and you count the number of events that occur in the climate change run, and then the ratio of the two numbers gives you this kind of increased probability. The problem is that when we come to talk about the really extreme events that people are interested in, such as the flooding in the Rhineland, such as the flooding in China, such as the big heat wave in British Columbia this year, such as the rain that hit New York, these are outside the range of what climate models can actually simulate. The models just don't have the resolution to be able to produce this level of intensity. So technically, you know, the answer is you've got 0 divided by 0, which is an undefined number, obviously. So, you know, I mean, what people tend to do is say, well, okay, this was a 10 sigma event in reality, so I'll look for 10 sigma events in my model. But of course, a 10 sigma event in your model might be a rather weak event in absolute terms. So my question really is, you know, as a neutral statistician, how does one best deal with this problem of the fact that the models are not, certainly the current generation of climate models are not accurate simulators of climate when it comes to looking at these types of extreme events?
Well, an initial reaction is just that to say this is use of relative risk, of course, is very widespread also in medical situations. But it may not be the right thing. Maybe one should be looking at an absolute difference in risk, partly for the reasons that you mentioned, but also because in the medical setting, to say that my risk of something terrible happening is increased by a factor of 10 because I've had a COVID jab, may not be a useful thing if the baseline risk of the terrible thing happening is in any way absolutely tiny. So it may not be the right measure of change, is the first point. The second is that the classical statistical approach would be to say, okay, what one should be doing is fitting a variety of distributions to the instead of just counting events, one should say, because inevitably the computation will be limited, and unless there's a reason to believe this event absolutely could not happen under the baseline no forcing climate model, it's probably unwise to say that because I've done 100 simulations or 1,000 or even 10,000, it could never happen. Maybe what one should be doing is fitting distributions to estimate the tails, and then doing some kind of sensitivity analysis to compare those ratios, or those probably those differences under those different scenarios. It's not a very helpful reply, perhaps, but it's the immediate reaction to this.
I mean, I have to say my concern is we end up with numbers like, the probability, some of these media numbers saying the probability's gone up by 20% or 30%, whereas actually if you really could look at this with a model that could simulate, we might find the answers in hundreds or thousands of % increase in likelihood. So it seems to me we might be really misjudging the impact of climate change on these extreme events just because our models are not good enough to simulate them.
Yeah, well, that's that. There's two issues. If you hoped that you could fit to the bulk and then use some of the extreme events to the extremes relative to that to extrapolate, then maybe that would be a more reasonable way to approach it. But of course, saying it's anywhere between something tiny and something huge isn't a very satisfactory way to generate a headline or to make the public sit up and take notice. Though perhaps it should be.
Thank you very much.
Pleasure.
Thank you. Is there a question from the audience here in the meantime? Andrea?
No question from
so
the wider community.
Me ask a question in that case?
Please.
So I'm a total outsider, both in statistics and in climatology, so this question may be completely off. And you introduced the generalized Pareto distribution, which I found extremely exciting and interesting. And you fairly showed that there is this parameter, zeta, I think it was, which seems not to be so well determined or not so easily determined. The question I have is, how sensitive are the results to zeta? So
they can be very sensitive, yes. So this is the crucial element. This is really essentially estimating the tail weight for the distribution.
Right.
And it's important to bring in information from outside if one can, or from other related data, or from prior knowledge, because that will constrain the value of eta considerably. And the same is true for the different types of spatial model one can fit. Again, if one can use external information such as that, we expect this process to be asymptotically independent. Of course, there are diagnostics for such things. That's also important.
Yeah, okay. Yeah, thank you. That clarifies things a bit. So if there are, there is a question. Wonderful.
Okay, Thomas.
Thank you very much. You've looked at an analysis of the ERA data set. Yep. There are many data sets from models as well. There are the CMIP5, CMIP6 analyses, a sequence of model generations. I was wondering whether in analyzing the statistics of extreme events, which you do, you also have, whether you've also looked at some convergence properties. If you look at new generations of models, can we make some robust statements out of looking at these analyses from a convergence type of view?
As in, are the extremes converging of these different classes of
Are
models?
moments of extreme distributions converging as we go to ever higher resolution
We haven't
models?
looked at that, no. I don't know if anybody has looked at that in the statistics world.
I'm not even sure whether it makes sense, but
Yeah, well, the difficulty is with moments is they're not usually a good measure of extremal behavior because these distributions don't necessarily have all their moments.
right.
So one would probably prefer to look at probabilities for rare events. But of course, then they have to be defined in somehow with respect to the center of the distribution because of uncertainties about where the distribution will be situated. And that somehow involves coming back to moments for estimating where the center is.
Or to these parameters like psi that you have
Exactly.
estimated.
Yeah, indeed.
Thank you.
Okay, if there are no further questions, then thank you very much again for a very insightful talk. And we move forward to Carrie Emanuel of MIT, who will tell us about effects of climate change on hurricanes, medicanes, and severe thunderstorms. I'll give you a 5-minute warning.
Thank you very much, Sami, and I'd like to begin by thanking the organizers for inviting me to this beautiful place for such an interesting conference. Like Anthony, this is my first live scientific conference in 18 months, and I must say I'd forgotten entirely how beautiful scientific venues are. So I actually would like to begin this lecture where Anthony left off in a sense, but by reiterating how important this problem really is. And I'll begin by simply reminding you of what the formal mathematical definition of risk is. It's the integral of cost over probability. It's a very simple statement. And you might think of one axis as being the intensity or some combination of the intensity and frequency of climate events, fires, storms, and so forth. And the cost typically goes up very nonlinearly with that event. If you have a 15 meter per second wind, it's not going to cause any damage. If you increase it to 20 meters per second, probably not very much damage. You increase it to 40 or 50 meters per second, everything changes. It's very nonlinear. So when you do the integral of cost over probability, you are putting typically a great deal of weight in the tails of the distribution. It's the tails of these event distributions, not the mean. Ask anyone seriously whether they care if the temperature goes up 1 degree. I don't. Okay, that's not what we care about. We care about the tails shifting and costing us a lot. And I think it's terribly important to understand that. But it presents a problem, which Anthony addressed, which is that when it comes to extreme weather events, we know from experience that over time, the most damaging events are those whose frequencies are roughly about once in 100 years. It's the steepest part of that curve, that cost curve. A few human generations, it's an anthropological question more than anything else. Turns out to be a few human generations. So if you take something rarer than that, say once in a 200-year event, and make it by climate change a once in a 50-year event, you get huge increases in damage. That's the interval we're concerned with for practical matters. But how are you going to estimate a 100-year event or a 200-year event if you have 50 years of data? A point that Anthony brought up, and I'm going to try to address that a little bit in my talk. And although it will be specifically about two phenomena, hurricanes and medicanes, which are sort of very similar things, and then severe thunderstorms, I want you to keep in mind this problem of the general issue. So I'm going to talk first about tropical cyclones and bring into the problem not just statistics, but theory, you might consider it to be the Bayesian prior, and observations. And then talk about using physics to downscale. Tim Palmer in his question rightly pointed out, a lot of the important phenomena are not well resolved or resolved at all by today's generation of global climate models. Downscaling is a technique for trying to get around that by embedding very fine resolution physical models within these global models, and I'll tell you about our efforts to do that in the case of hurricanes. I'll talk a little bit about another phenomenon which interests me and which is not as well developed in the literature, which is severe convective storms, and talk about some theoretical considerations and then wrap things up. So let's begin with a little bit of theory. There are some things we understand fairly well about the physics of tropical cyclones, and I wish I had time to talk to you about those physics because they're very interesting. One of them is that there's a very definite thermodynamically imposed upper bound on how strong the winds can be in a given climate. And we call that the potential intensity. It actually can be developed from a variation on Carnot's famous theorem about heat engines. And the potential intensity works fairly well as an upper bound. So this is a little bit hard graph to read, but the x-axis is month of the year. And you're looking at a compilation of data from the western North Pacific Ocean. And the blue line at the top, that you see that blue curve, is from climatological data, this thermodynamically measured property called the potential intensity. And then the bars that you see going across there for each month are an observed range of actual intensities of observed typhoons in that region. The dots are the 95th percentile of those distributions. So indeed, the potential intensity is really acting as an upper bound. In practice, very few storms actually reach that, but it turns out, and I could show you more data, that if you have a sufficiently large collection of these events, their mean intensity scales with the potential intensity. So we can use climate models to predict how this thermodynamic bound will vary, among other things, even if we can't resolve the storms themselves. Now, this is a map simply showing the annual maximum potential intensity from climate data for the present climate. And it's an upper bound of a wind speed in a hurricane, and you can see that, as you might expect, it's very large in the tropics, and it encompasses most of the areas that experience tropical cyclones. Because it's an energy bound, the theory is unaware that tropical cyclones are mechanically impossible on the equator or near the equator. But we can account for that. Everywhere else, it works very well as an upper bound. And that bound, as had been predicted 30 years ago, has been going up. This is simply the trend in this upper bound from 1979 to 2018, based on climate analyses. So it's in meters per second per century is how this trend is expressed. And I'm only showing you this trend where it's significant with a p-value less than 0.05. So the green areas don't have significant trends. But basically, the tropical cyclone generation regions have been experiencing an increase in this upper bound. If you then calculate the upper bound from climate models going forward, this is a particular climate model, same kind of map, this is a projected trend. And you can see likewise, one projects a continued upward trend. This is not something you need a climate model for. This is this basic theory, coupled with a theory about how climate change responds to increasing greenhouse gases. So with a little bit of theory, you can do something. This doesn't tell you the whole story by any means, but you can say something about some aspect of hurricanes, namely their speed limit is going up. So I would summarize inferences we can make from basic theory as potential intensity goes up when you put greenhouse gases in the atmosphere. And we would infer from that that the incidence of the very highest intensity storms should go up. But we can't make general inferences about the frequency of all storms based on this. Tim said you could have a very large increase. I would argue it can be infinite. Because if the current bound is, say, 100 meters per second, you'll never see storms more than 100 meters per second, and you raise it to 105, and you look for the incidence of 105 meter per second storms, it goes up by a factor of infinity because you started from 0. And this is the problem about looking at tails. For reasons I don't have time to describe, the theory also predicts that these increases in general should be larger in the subtropics than in the deep tropics. And then this is very important. Another very old thermodynamic relationship called Clausius-Clapeyron says that if you raise the temperature of the air by 1 degree C, you raise the amount of water vapor at saturation by about 7%. And this can be used to show that in heavy rainstorms, not in rain in general, but for the extreme rain events, we expect those to go up at the Clausius-Clapeyron rate, and we're seeing that. And since in these storms, by far, the most lethal aspect of hurricanes, severe thunderstorms, many other kinds of storms, is water, not wind, even if it's a very high windstorm. As we've seen in very recent examples in Louisiana and New Jersey, it's the water that you can't care about. We expect to see this go up very quickly, and then arguably we are seeing it go up. We're seeing wind speeds increase as well. I'm going to, for the sake of time, skip over this slide. So can we, armed with physics, say something about changes in tropical cyclone activity? Now, statistics are fine, and they're very necessary, but one of the potential hazards is that if you are using historical statistics to estimate extreme values, and perhaps using generalized extreme value theory, or whatever you like to do, there is a fundamental assumption in the background that those statistics are stationary. If they're not stationary, you have a bit of a problem. One way of getting around that is to use the physics of the problem to estimate how these extreme events will change, and I'm a huge advocate of that, because we are living in a time of very non-stationary statistics of extreme events. And physics is another way of knowing the world, not just observations. And the physics better be consistent with the observations that you have, but you can extrapolate using physics to environments you have yet to encounter that you don't have historical records for. Now, I wish I had more time to tell you how we do this in the case of hurricanes. There are a lot of publications on this I could refer you to, but basically the idea is to embed within the global climate model framework specialized models of very, very high resolution that are known to be capable of resolving the wind and rainstorm of a hurricane. We embed those in the time-evolving three-dimensional atmosphere ocean systems produced by global climate models. We use a particular coupled ocean atmosphere model to model a hurricane properly. You have to allow for the fact that the ocean underneath it responds to it. You can't hold the ocean stationary. And we use a model that was originally developed to help forecast actual hurricanes in real time. And one of the interesting tricks of extending this to a climate is that how do you actually decide where and when there's going to be a hurricane? In this case, believe it or not, we randomly seed the global model in space and time with a very large number of, you might think of them as proto-hurricanes, initial hurricanes. And you use your embedded hurricane model to decide whether their intensity goes up or down. The vast majority of them are predicted to die. And you regard the survivors as the climatology. So it's a kind of natural selection mechanism, an analogy to biology. It's not really the survival of the fittest storms, but it's the survival of the storms put in the fittest environments. And if you run this in the current climate and compare it to the observed hurricane climatology, it works extraordinarily well, much better than one has a right to assume that it would. And you can generate 100,000 storms easily. And you can say, well, I'm interested in Rome, and generate 100,000 storms filtered so that only those storms reasonably close to Rome are included in the data set. So you can get around the statistical problem, in some cases anyway, using the physics of the situation. So here is a map of only 1,000 tracks. This is out of a much larger data set because you have a plotting problem if you want to try to plot 100,000 tracks. These are tropical cyclone tracks all around the world from something like the present climate. And we know from very extensive comparisons of the properties of these storms to real storms. Whoops. For example, this distribution, which shows the exceedance frequency, the number of storms that exceed the wind speed in the quaint unit of knots in this case that you see on the x-axis, as a function of the value on that axis. The blue is from a limited number of historical tracks. The red is from the synthetic technique. And the green bars show the expected sampling error. That is, if you resample the much more numerous synthetic events at the rate of the historical events, you expect 90% of those subsamples to lie within those green bars. Here is another test. Can it predict the seasonal cycle of these storms? Here is a graph showing the seasonal cycle of tropical cyclones in the North Atlantic. The blue dots are from historical data. The red curve is from a much larger set of synthetic tracks. And the blue shading is, again, an estimate of the sampling error of the historical tracks. Now, I'm going to show you some new results now that are actually about the past rather than the future, but they interest me greatly. Are hurricanes increasing in the North Atlantic Ocean? Only about 11% of the world's hurricanes occur there, but they're very important because they affect a lot of populated areas. A lot of inference has been tried to be made from the historical data set, which, believe it or not, goes back to 1851. But as you go back in time, the observations become less and less numerous, more and more error-prone. And so using the historical database, and people have tried very, very hard, including actual historians, to get it right, it's fraught. So what we did was we used a climate analysis driven only by observed ocean temperatures to drive a climate model, something called a 20th century reanalysis over the same period of time, and then use the downscaling technique I've just described to estimate the number of hurricanes in the past. Okay, and this is what we get. So this graph goes from the middle of the 19th century to more or less the present. And the blue curve you see there is the best shot that this historical reconstruction has for Atlantic storms. I'm showing you a time series that's been smoothed here with a 7-year running average. So you're only looking at variability on timescale somewhat longer than that. And the blue dashed line is just a Poisson regression of that. This is the number of storms making landfall anywhere in the North Atlantic basin. Islands, coastline, Mexico, US, wherever, in the historical base. The red curve is simply, and it's completely independent of the blue curve in terms of technique, is using climate data to drive this downscaling technique over the same period of time, likewise with a Poisson regression curve, and then an estimate of the sampling error, basically the same technique in the red shading there. And people have always thought that the historical estimates from early in this period underestimate the number of storms because there were so few observations. They're right. And according to this analysis, yes, you see a divergence going back in time with fewer historical events than would be quote-unquote predicted by this technique. And yet, there is still a large upward trend. And to be quite honest with you, I have no idea why there is an upward trend like this. It's not something that's easily rationalized, and I can come back and talk about that. This is exactly the same thing, but using a different European-based climate analysis. Okay, again, this is a large-scale climate that's used to drive this downscaling. The blue curve is the same as before, but this European product is for a shorter interval of time. It only begins in the year 1900. But basically the same fairly good agreement between the downscaling and the observations. We do understand, and this is a story for another day, that this pronounced dip in activity in the North Atlantic from roughly the 1940s to the 1990s is a man-made hurricane drought. This is a fascinating story, nothing to do with greenhouse gases. but a byproduct of the fact that we were putting a lot of aerosols into the atmosphere. These are sulfate aerosols, highly reflective. It's a long story. By an indirect mechanism, they managed to cool the tropical Atlantic during the summer and thereby curtail hurricane activity. And this huge uptick that everybody agrees has occurred since about the 1980s is not global warming. There might be a little bit of a global warming signal there. It's principally a consequence of the Clean Air Acts that were passed in Europe and North America. And no, I'm not telling you that we shouldn't have passed those acts, but this has been a black lining on an otherwise silver cloud, I would argue. A story for another day. Now, if we apply the same technique I just described to you to the global record, not just the North Atlantic, it's easy to do this globally, we essentially see no trend. So at the left, you see the number of tropical cyclones downscaled from 3 different climate reanalyses, going back to 1850. And on the right, the number of so-called major or intense hurricanes. And in neither case are the trends, if there are trends at all, statistically significant. So we don't see globally much trend in the downscaled events. I'm not showing the observations because globally the observations are only reliable back to about 1985. There's no use putting that on here. Unfortunately, we just don't have good hurricane data outside the Atlantic much before 1980. If we apply the same technique to 9 of the most recent generation of climate models going forward, this is happens to be showing the frequency of Category 1 tropical cyclones. The blue is downscaling the historical period as simulated by these models. The red, the same thing, but assuming that CO2 is increasing by 1% per year. And the shading showing the scatter among the 9 models. We do see a upward trend in this particular metric in the future, even though it's too small to have detected by now, if that were indeed what was going on. And let me turn briefly to metacanes, which we are fairly sure are the same thing as tropical cyclones, although forming under rather special rather than rather normal conditions. You have to have just the right conditions to have a tropical cyclone over the metacane. This is a picture of metacane Zorba that hit Greece in 2018. You can even see an eye in the storm there. We applied a similar downscaling technique to that, to many, many different of the last generation CMIT-5 climate models. And what you see at the top with the diagonal shading showing regions of statistical significance is the average change in the frequency of such storms out to the end, projected out to the end of the century, with blue showing a decrease. So over most of the Mediterranean, including here, we expect fewer of these events, the red showing an increase. Big increases in the Black Sea. We had, for the first time that I know of, a tropical cyclone in the Black Sea just a few months ago. The bottom shows the change in frequency of winds greater than about 30 meters per second. And there you see red everywhere. So these storms, as the theory would predict, are getting more intense, but not necessarily more frequent. Polar lows is a similar phenomenon at high latitudes, up to the north and west of Norway, for example. There's a satellite picture. Apply that technique to polar lows, and it's very interesting. If you look at the bottom left, this is the projected change in the frequency of such storms. Big declines in the area where they're now fairly frequent to the south of Iceland, but some increases along the Norwegian coast. So there's not some blanket statement one can make about the frequency of these storms going up and down. It's very regional. At the end of the day, all climate change is local. Now I want to wind up with a discussion of something completely different, which is severe thunderstorms. These kill about 500 people a year around the world and cause a great deal of damage. And so they're of some social concern, but there's very much less research done on this phenomenon. And if you think the damage and so forth is bad, there are even worse consequences, as far as I'm concerned. Here is a picture of what happened with a particular hailstorm destroying 8 million bottles worth of champagne grapes. When I saw this headline, it really motivated me to try to understand this phenomenon better. Okay, here is the current global hail climatology. And you can see that hail occurs in some very special places. The central part of the US and Canada, the Pampas of Argentina has many hailstorms. Equatorial Africa, the Sahel, the southern boundary of the Mediterranean, Bangladesh, and the far northern parts of India and Pakistan, and there are a few other places. One of the things that you notice if you're a meteorologist or a climatologist is that these storms tend to occur in regions of strong gradient in soil moisture, going from very dry lands to very wet lands. For example, going west to east across the plains of the US or Pampas, okay? So why do we have that climatology? Believe it or not, that's not a very well answered question in meteorology today. And so we had proposed a hypothesis that one of the ingredients you need for these storms is a lot of stored energy in the atmosphere called convective available potential energy, or CAPE. And we hypothesized that large CAPE is produced when you take a very deep adiabatic layer that you might produce over a desert, for example, and advect it or move it over wet soil. This is actually kind of a new idea. It was always assumed that what you need to do is advect it over moist air, but we think the soil is essential. Thank you. So this is a diagram showing temperature falling steeply with height or with pressure equivalently. In a desert air mass, you might think of that scale as covering 5 kilometers or so on the vertical axis. Temperature goes down to about 1 degree C per 100 meters in dry air that's been heated from below. It's an adiabatic lapse rate or a critical lapse rate, you might say. If you take that air and move it over moist soil, the first thing that happens is evaporation of water from the ground cools the air. So you get the new profile that's shown in blue here. And it's very stable. If you take a sample of air from near the bottom of that profile and lift it up, it's negatively buoyant through its whole trajectory. There's no energy. But if you now turn on the sun rises over that wet soil, it heats up the air, water evaporates and moistens it, you might get something that looks like the red profile. And that's the sort of profile that's conducive to a hailstorm. It's cool at the bottom, but much warmer at the top. If you lift a parcel adiabatically, it follows that red line. And it's cold in the base, so it's stable, but it's only metastable. If you lift it above where it crosses the black line, it becomes warm and unstable. That potential barrier allows this convective available potential energy to accumulate, and that's critical. Otherwise, it's just released immediately. So you need to make an atmospheric bomb, basically. You have a potential barrier that prevents, not in this case, not a chemical reaction, but an atmospheric instability from developing. And so we call the energy is actually proportional to the area between these curves. You can show that. You call that negative area the inhibition, the convective inhibition, or CIN, and the positive area the CAPE. And so you can actually work out through a very simple model, an expression for an upper bound on CAPE produced this way. It's a complicated expression. But the important term that I've got an arrow to is the saturation water concentration of the lower atmosphere. And that scales with Clausius-Clapeyron. It goes up literally exponentially with temperature. That's the mean wind speed at the surface, and CAPE increases as you reduce that. And that's the availability of moisture, and CAPE increases as you increase that as well. So you want moist soil with lots of wind blowing over it, and then you have this situation. So let me summarize. There's a lot more interesting physics than I've been able to tell you today, but I would argue that even if you had a Gaussian distribution of extreme events, and you don't usually, but supposing you did, shifting that Gaussian uniformly without changing its shape, the percentage changes are obviously much larger in the tails than near the center of that probability distribution. So extreme weather events are also, in addition to being the thing you're concerned about, kind of a harbinger of climate change because they're the things that change most radically early in the process, well, through the whole process, actually. Tropical cyclones and severe convective storms are among the most damaging of these extreme events. Just simple theory tells you that the speed limit on hurricanes goes up, and so you expect a greater frequency of the high intensity events. Observations show that the limit is going up. We can use physics to model storms, I would argue, and very carefully compare them to observations, so you have some confidence in the model. But once you have it, you can generate such a large number of such events as to get around the strictly statistical limitations that are owing to small numbers. Severe convection depends upon, among other things, on the stored energy. And the way to get this stored energy is to advect deep, dry adiabatic layers formed over deserts, over wet soils, and then heat them by the sun. And the peak values of both this energy and the inhibition potential, CIN, scale approximately with the Clausius-Clapeyron equation, 7% per degree C. Naively, at least, we would expect from that to have fewer severe convective storms in the future because of this greater inhibition, but stronger ones that do form. And so I'll leave you with those thoughts. Obviously, happy to answer any questions. Thank you.
Thank you very much. Yes, thank you very much for this very insightful presentation. I'm sure there are a number of questions. Nobody dares to go first.
Thank you so much, Carrie, for this great talk. I have a couple of questions. One is, do we have now a better understanding of what constrains the number of storms that we get every year? And so this is my first question. The second question is that you mentioned the Clausius-Clapeyron scaling as rain associated with hurricanes, and I was wondering if we expect that or a super Clausius-Clapeyron scaling through changes, for instance, in the dynamics.
Right. Good, thank you, Simona. The frequency issue is still hotly debated in research. We don't really understand the frequency very well. It's dominated by weak events that aren't very destructive, so from a practical point of view, we're more concerned about the strong events. But to be honest with you, we have a paucity of even theories about why we have approximately 80 tropical cyclones on the planet. And that's a big limitation on anything. The modeling I just described simulates that number pretty well, although you have to calibrate it. But I don't think that translates so easily into understanding. All right. Your second question, I think, was about the Clausius-Clapeyron scaling of hurricane rainfall. Well, that's basically a very simple physics, that if you have such a strong updraft, and you know what controls the speed of that updraft, basically all the rest you need to know for the rate of rainfall is the amount of water at saturation.
I was wondering if dynamical effects or microphysical effects might give you a super Clausius-Clapeyron scaling.
Yes, they could. We don't observe that for tropical cyclones. It's a story for another day, but I would argue, based on work I did in Italy a few years ago, this is a very, very interesting question. What determines the speed of an updraft in a thunderstorm? At least a thunderstorm over the ocean. The answer, we think, and you'll be shocked, the answer is the terminal velocity of raindrops falling through air. That's what we think the answer is. That doesn't vary with climate. And that's why it turns out to be more strictly Clausius-Clapeyron. Yeah.
Thank you.
Okay.
Great. Are there any further questions from the floor or from?
And not so far from the floor. There's Timothy Palmer again.
Okay.
Okay.
Let's hear
Be
it.
connected.
Hi, Kerry. Sorry to be hogging the questions. I hope I'm not hogging them too much. But I was kind of interested in your comment about the aerosols in the 1960s, because it's not something I personally know much about, but I know it's been a topic of controversy. The Met Office have claimed, I think for some years now, that the cooling in the North Atlantic has been the consequence of aerosols, but I know GFDL have come out very strongly against that. So I guess my question is, do you have some new evidence that is pointing us in the aerosol direction that would, I don't know, maybe counter the GFDL arguments against?
Yes, thank you, Tim. We do have new evidence. I wish I could had given a talk about that. If it were a more technical conference, I would have. It's very interesting. It's well understood that the European aerosols in the summer are carried down by the airflow over the Mediterranean and northern Africa. And there was a pronounced actual drought in the Sahel region of Africa during the period of high aerosols. That drought in the Sahara led to a great deal more lofting of mineral dust from the desert. That's well documented as well. And that dust is carried westward over the tropical Atlantic. And it was actually the mineral dust optics that cooled the Atlantic more so than the sulfates. So it answers the GFDL objection. The GFDL point was, well, yes, it's in the right phase, but the direct effect is not nearly strong enough. I think they're right about that. But there was this knock-on effect that we've discovered more recently that's responsible for this. Yeah. It's an interesting story. And it's
very interesting. Yeah. I'll have to talk to you sometime about that. Thank you.
Sure.
So, Andrea, there is a remote question.
From a Zoom community. It's from Nicolas Caffetta that sends this message. The annual number of large Atlantic hurricanes from 1878 to 2020 actually show a significant 60-year oscillation that is found to be well correlated with a 60-year Atlantic multi-decadal oscillation, AMO. Once that the hurricane record is also corrected for missing events in the past, Vecchi Knut's Journal of Climate, 2011, showed that the period 880, 890, 1940 to 1960, and 2000, 2020 had nearly equivalent number of total large hurricanes, and there's a link to that. Thus, there is a good correlation with the natural oceanic climatic oscillation, but not with a CO2 monotonic increase during the 20th century, nor with a warming predicted by the models, although they predict a small cooling around 1960 because of aerosol. But the AMO shows a 60-year oscillation, and Knutz and al. Paper in 2011 showed that such AMO oscillation lasts for 8,000 years, which likely generates an equivalent hurricane oscillation.
Yeah, there's a lot in that question. I don't know if I will remember enough of it.
Don't hold it on me.
Yes, I'm speaking to the questioner. But we used to think that the Atlantic multi-decadal oscillation was responsible for this dip I described as a hurricane drought. But we don't believe that anymore because we don't find strong evidence for it. And even the person who coined that term, Michael Mann, has written a paper recently in Nature where he says, no, that has very little to do with what's happening in the tropical Atlantic. The Vecchi et al. Paper that you quoted, or the questioner quoted, if you read it carefully, what it's doing is it's not saying that the tropical cyclone counts in the North Atlantic were constant. It's subtly different from that. It's saying that based strictly on historical observations, you cannot decisively rule out the hypothesis that the tropical cyclones were constant. It's a very different thing. I would argue that they can't rule out also the hypothesis that they've been increasing. And so it comes down to what you believe to be the proper null case. And if all you had were historical observations, I would agree the proper null case is no change. But from a Bayesian point of view, we now have, I would say, a strong prior, which is that they have been increasing. And the Vecchi and Knutson method probably cannot for the same reasons, rule out that they have been increasing. It's a very different sort of statement. I don't disagree with them, but it's very easy, unfortunately, for the media to transform a statement. Historical observations do not suffice to rule out the null hypothesis into a statement that there's been no change.
Any more questions from the floor?
I think it's one coming, but if some...
Otherwise, I'll briefly ask a question. You showed for the Atlantic hurricanes, if you could show that graph again, depending on whether you take directly the observations or have them corrected with the modeling for the expectations.
This one?
Yes,
Yeah.
for example, this one. Could you show the screen, please? Yeah, thank you. So yes, there seems to be this increase, and I agree with that. If you take the red curve, however, have you studied how sensitive it is to your starting date? Because the end date is obviously fixed, but the starting date is more or less, you know.
So
because it's oscillating a lot, that could have an effect.
Sure. It's important to understand that this red curve is not a time integration of something. It is downscaled from a global climate model, which is a time integration. And to answer your question, these climate models are typically run many times, including the reanalyses, as an ensemble. And this is showing you one ensemble member. Now, I haven't shown you in the slide deck, but I have done for one. It's actually hard to get your hands on the other ensemble members for these kinds of analyses. I have done so for one of them. And the details are different, but not the overall upward trend, nor the drought is very robust, and the upward trend is robust. Yeah. Okay. The finer details do change from one ensemble member to the next.
Right. Has another question come? No. Well, then I think you're also, perfectly on time. Thank you very, very much again. And we move on to the final speaker of this session, Simona Bordoni from the Università di Trento, who is going to speak about regional precipitation changes with warming. I'll give you 5 minutes more. Okay.
Good afternoon, everybody. As everybody else who spoke before me, this is the first conference I attend in 18 months, and it was not obvious to me at all that the first conference I would attend again in person after the pandemic would be such a great conference with so many prominent speakers. So I feel very honored and humbled, and I really thank the organizing committee for putting me on this amazing list. And it's even more humbling giving this talk after Carrie's. It's really a tough act to follow. So today I'm going to be talking about an open challenge in the climate sciences that is that of reducing uncertainties in regional climate projections. And I'll focus primarily on projections of precipitation. And that is because, at the end, those are the ones that really have the largest impacts. Those that really have those are the ones that we need to adapt and mitigate. And so these are really the ones that we care about. This is really a challenge that motivates a lot of my research efforts. I spend a lot of time thinking about the interaction between the large-scale atmospheric circulation and the Earth's hydrological cycle, really with the final goal of advancing fundamental understanding that eventually might help us to reduce the uncertainties in these projections. And I'm also going to be a little bit more precise as to what I mean by regional, because not everybody interprets that word in the same way. So let me start off with something very basic, and let me show you the distribution of the long-term annually average precipitation over the Earth's surface from a specific data set, GPCP. So as probably we all know, the most intense rainfall falls over the tropical oceans, over which intense rainfall is primarily organized along bands that are narrow in latitude but extended in longitude. We refer to these features as intertropical convergence zones, or ITCZ. So we also see intense rainfall over tropical and subtropical land masses, and we will see that, especially as we move away from the equator, this is really the imprint on the annual average of a strong seasonality of precipitation there. And then outside of the tropics, precipitation is primarily organized along storm tracks, tilted rainfall bands that are primarily focused over the oceans but do affect the nearby continents. And here I'll primarily focus on the tropics because this is really the latitude bands where I spend a lot of time, at least research-wise, not being physically there. If now, in addition to a temporal long-term mean, for each latitude, we also take an average in longitude, we find this distribution of the zonally average precipitation as a function of latitude, and we find the very familiar pattern of alternating wetter and drier bands, with the wettest band being over in the tropical regions, the driest in the subtropics, and then we found two other wet bands in the extratropics of both hemispheres. So this is, I think, as basic as you can get in terms of characterizing the Earth's hydrological cycle. And yet there are aspects of this distribution that have remained debated until very recent time. One of these aspects that I would like to emphasize here is the fact that maximum rainfall does not fall on the equator, but in fact is shifted northward of the equator at around 6 degrees for present-day climate. Nor is this distribution symmetric about the equator. This, of course, suggests that there must be an underlying asymmetry between the two hemispheres, which favors, in terms of where the precipitation falls, the northern hemisphere. And what is this underlying asymmetry? What is really the driving asymmetry is something that has remained debated in the literature until recent times. And I would say that consensus has emerged in the past 10 years or so, primarily thanks to our advances in the theoretical understanding of controls on tropical precipitation. And this asymmetry doesn't have anything to do, at least we believe so, with the distribution of the land masses. That is a plausible hypothesis, right? The fact that we have more land masses in the northern hemisphere, but it turns out that really the driving asymmetry comes from the ocean, how it transports energy from the southern to the northern hemisphere, therefore making the northern hemisphere slightly warmer than the southern hemisphere. Focusing again on these zonal averages, and again with a specific focus in the tropics, it is clear that these patterns of zonally average precipitation are strongly tied to the atmospheric circulation and the atmospheric overturning that in the tropics, in the pressure latitude plane, takes the shape of two cells, the Hadley cells, that are almost symmetric about the equator, ascending motion nearby the equator, descending motions in the subtropics. And it is clear that these overturning circulations really have a strong impact on this patterns of precipitation that we've just described, with the ITCZ being collocated with the ascending branch, the subtropical dry zones being under the influence of the descending branches of the Hadley cell. Let me emphasize how it is therefore clear how important features of the circulation, again, the position of the ascending branch, the strength of this returning, the extent of the cells, really again play a very important role in shaping the precipitation distribution, and yet we don't have close theories for how these characteristics of the Hadley circulations will respond to changes in the mean state climate, which might help us guide the analysis of the observational record and, of course, model output. Let me go back to now looking a little bit more at the seasonality. Again, I spent a lot of time thinking about seasonal variations of tropical rain bands in a way that I will describe later. And so let me try to show you some aspects of the seasonal cycle by now showing you the distribution of the long-term mean precipitation, but now focusing on the solstice seasons. So July, this is the northern hemisphere summer, and the corresponding one for January, southern hemisphere summer. And I'm gonna be toggling between the two, again, focused primarily in the tropics. And not surprisingly, probably you see that the precipitation tends to follow the sun, in the sense that this rainfall belts tend to move towards the summer hemisphere. But also notice how there is some contrast between the land and the ocean. In the ocean, the seasonal cycle is somewhat muted, both in terms of intensity and location. And also notice how over significant stretches of the Pacific Ocean, in fact, maximum precipitation remains north of the equator, even during southern hemisphere summer. Now I want to focus your attention on subtropical land masses. Pick your continent of choice. One obvious one to look at is Southeast Asia. And notice how there, the seasonality is way more dramatic. We have very dry winters being followed by very wet summers. And it's really this movement of the tropical rain belts into the summertime subtropical continents that we now understand is associated with the development of monsoonal circulations there. And in fact, we not only have the Indian monsoon, which you might all be familiar with, but we have monsoons in the northern hemisphere over the Sahel region, over North America, and corresponding monsoon systems in the southern hemisphere. And in fact, monsoons have been studied as regional systems for many decades, somewhat separately, but it has now become evident in the past 20 years that monsoons really are a regional monsoon systems are a regional manifestation of a global monsoon, a dominant mode of variability of the atmospheric overturning circulation as associated precipitation patterns in the tropics in response to the seasonal cycle of the insolation. And let me try to make this point a little bit more clear, in particular this connection between local monsoonal circulations and the global Hadley circulation. So this is what the July overturning circulation, again on the pressure latitude map, looks like if you take a global zonal mean. So the two-cell pattern that dominates the annual average that I showed earlier is being replaced by a solstitial mode that is characterized by a single cell, which is really the dominant cell, which is the, in this case, the southern cell, the winter cell, that now has strengthened. It has also expanded so that its ascending branch is now well into the northern hemisphere, that is the summer hemisphere. And you would also have a summer cell, but it's so narrow and so weak that actually you don't see it here because of the choice of the color of the contour intervals that I chose to show this very strong cross-equatorial Hadley circulation. If now, instead of looking at a global average, you just average in longitude over the longitudes of the Indian monsoon, that is between 60 and 100 degrees east, this is what you get. You still see that over July, when the monsoon has reached maturity, the atmosphere locally, regionally, recirculates in this pressure latitude plane in a cell that looks very much like a cross-equatorial Hadley circulation, with the monsoonal precipitation being embedded within the ascending branch of this cross-equatorial cell. And in fact, I think that work that I have done, but also many other brilliant scientists have contributed to these advances. I think that it's now become clear that we should think about at least large-scale monsoons as cross-equatorial Hadley circulations that project strongly on the solstice zonal mean. So we have described this somewhat regional, but still very large-scale precipitation patterns, and it is a fair, from the observations, it is a fair question to ask to what extent do state-of-the-art climate models that we use to make projections are able to simulate these patterns. And this is taken from the 5th assessment report based on CMIP5 models. This is the multi-model mean precipitation, so you see that definitely these models do capture the basic features, but they do so with non-insignificant biases. Where you see blue, models tend to overestimate precipitation. Where you see brown, underestimate precipitation relative to observations. In the tropics, you see a lot of blue over the ocean, a lot of brown over land. Also notice this bias, which is called the double ITCZ bias, which has been very stubborn, has persisted through generations of climate models. Most models overdo the precipitation that falls over the southern Pacific Ocean. So I couldn't find this version of this estimate from the just released 6th assessment report that has been discussed already earlier today. But let me show you results based on CMIP6, that is the models that have been used for the 6th assessment report from colleagues at MPI. Again, this is the multi-model mean precipitation from CMIP6, and this is the bias relative to TRIM, another observational record based on satellites in the tropics. And again, notice how also here the interval scale is larger, so in many ways
we see very similar biases that we had in CMIP5 have persisted in CMIP6 models. So how about projections? Again, these are how precipitation in terms of percentage change relative to the end of the 20th century are projected to change at 2 different time slices, mid and end of the 21st century under the RCP 8.5 scenario. Again, where you see blue, wettening tendency, where you see brown, drying tendency. You see there is blue, there is brown, but maybe, and those are big changes, but maybe the point that I really want to emphasize here is that you should be looking at the regions with the hatching and the region with the stipplings, that is the dots. Where you see hatching, this is where the force signal has not emerged over the internal variability. The stippling is where, in fact, that signal has emerged, and there is also a good level of model-to-model agreement. I'll let you decide how we are doing in terms of projections for the tropics. And this is, and I'm sorry, but this is what I could find from the most recent 6 assessment report in terms of projections. And again, those is not a finalized version yet, but again, similar projections based on one emission scenario, well, shared socioeconomic pathway scenario, again, mid-end of the 21st century. And again, notice how the hatching here as always represents where there is not a high level of model agreement. I don't know if you can see, there is also some regions where you have crosses, which is where the signal is conflicting, even in terms of the sign of the projected response. So again, there is still a lot of uncertainty in projections of these large scale features when it comes to tropical precipitations, and in fact, this can be said for a lot of other regional scale changes. So here, just a summary, if you focus on monsoons, again, taken from the 6th assessment report. So we assess the near-term changes in global monsoon, precipitation, and circulation will be affected by the combined effects of model uncertainty and internal variability, which together are larger than the forced signal. So these are for the short, near-term changes. If we look at the longer-term changes and of the 21st century, it is likely that the monsoonal precipitation will increase with increase in the global mean surface air temperature despite a weakened monsoonal circulations. But there are differences between models and there are different responses across monsoon regions. The uncertainty remains large. So this is a little bit of a depressing state of affairs, right? So you might wonder, is there anything robust that we're able to say about changes in the Earth's hydrological cycle? And there are some robust responses. And here, I really want to emphasize how most of those are really based on physically based principles. And I'll try to go back to this point, how it is really important not to just to be able to simulate, but also to physically understand the fundamental driving mechanisms, because these mechanisms, these physically based hypotheses, provide a way to interpret even responses across models that might be different. And so what are these robust responses in the Earth's hydrological cycle? So we know, and this is something that has been known for decades now, that the global mean precipitation increases at a rate of about 1 to 3% per degree of warming. And this is, for instance, again, taken analysis based on the CMIP5. So we are averaging over the entire globe across different models, different scenarios, also a little bit different averages. And again, you see that in general, this is what is being predicted. 1 to 3% increases in global precipitation per degree of warming. Kerry has already talked about the Clausius-Clapeyron relationship, which provides a scaling of about 7% of the degree of warming. This is how rapidly with warming the atmospheric moisture content is increasing. So notably, the rate of increase of the global mean precipitation is smaller than the rate of increase of the atmospheric water vapor. Why is that? That is because, and again now this is something that we understand very clearly, is that globally when we take a global average, precipitation is not constrained by the availability of moisture, but is constrained by the availability of energy. And this, for instance, also allows to understand one result that Thomas showed this morning, looking at, for instance, geoengineering impacts on the precipitation response. even if, again, assume that we pump sulfate aerosols in the stratosphere, which reflect the incoming solar radiation. Let's suppose that we do it in a way that completely counteracts the warming due to greenhouse gases. Yet, because we are changing the energy budget, we will expect changes in the precipitation, both at the global and regional scale, even without any change in the temperature. So these, of course, should also raise some other concerns about some changes that might be not predicted in response to geoengineering schemes. Okay, so global precipitation is limited by energy, but as we go down to more regional scales, and again, here by regional, I mean still continental scale, ocean basin scales, we're talking about thousands of kilometers, but as we start going down from the global to regional perspective, this is where precipitation, and in particular net precipitation, the difference between precipitation and evaporation really starts being constrained by the availability of moisture, primarily through convergence or divergence of water vapor flux by atmospheric motions. And so is there anything that we can say? Well, it turns out that if we assume that relative humidity remains constant, and there are some reasons to believe that relative humidity will not increase greatly with warming, and we also assume no circulation changes, then we can predict that dry regions will get drier and wet regions will get wetter through this Clausius-Clapeyron scaling. That is, we have an amplification of the hydrological cycle. Does this provide any guidance when we look at projections from climate models? And this is what is shown here. So these blue curves represent the change in P minus E, again, difference between projections for the end of the 21st century and the climatology from the end of the 20th century, from, I think, 3 or 4 different climate models participating in CMIP6. And I won't go into the details, but these 2 lines here represent theoretical fits, simple estimates that are based on some forms or others of this Clausius-Clapeyron scaling, what we call the thermodynamic scaling. So at least when we look at the zonal patterns of precipitation changes, the thermodynamic response does capture at least some of the most important patterns. Of course, things start to break down way more when we start looking at variations with longitude, and that is because at the regional scale, it's really the dynamics that dictates a major part of the regional changes. And dynamics here, I mean atmospheric circulations and weather statistics, and changes in this circulation pattern. So it's really the dynamic response due to changes in atmospheric circulation that remains highly uncertain because it has been very hard to constrain from a theoretical perspective. And so how do we make progress in this? And so some approaches that have been taken by the community and that really emphasize climate dynamics as a way to reveal maybe the best simulations and identify the most relevant model errors and way to reduce or mitigate them. These errors include the use of large ensembles, and these have been particularly useful in trying to separate the uncertainty associated with errors in models from that associated with the internal variability. The use of emergent constraint analysis, which relates present-day observable parameters to projected uncertainties, and then regional downscaling of global projections. In addition, of course, a lot is going on in terms of thinking about how to best improve our modeling capabilities, and some next-generation Earth system models that have been recently proposed, and this is a project that got funded, just started as of September 1st, I'm also part of, is thinking about having cloud resolving, storm resolving, I should say, not cloud resolving, storm resolving global Earth system models as a way to maybe really have an opportunity by resolving scales that have not been resolved yet to really make significant progress in the next decade or so. So I'll be happy to take more questions about what we have learned through these different approaches, but here I would really like to emphasize my own personal approach, one that I try to always go back to, no matter what specific phenomenon I'm interested in. And this is really to emphasize how a lot of our advances have really been based on simpler, more idealized models rather than the models with full complexity. So it's always go back and again, leverage the model hierarchy in a way that I will try to emphasize, and of course this is just a personal view, together with the theoretical frameworks that are physically based. And again, because I look at larger scale circulations, I focus a lot on large scale budgets of moisture, energy, and angular momentum that we will see can provide some important constraints on how we think the circulations are going to respond. So what do I mean by the model hierarchy? So on the one end of the spectrum, we have the comprehensive GCMs. In fact, we don't even talk about GCMs anymore. We talk about Earth system models, ESMs, that have become more and more complex. And one model that really resides on the opposite side of this parameter space that I really like to use extensively is a much simpler, a much more idealized general circulation model. And it's basically an atmospheric GCM coupled to a lower surface completely covered by a passive ocean. This is what we call an aquaplanet. This model is idealized not only in terms of the configuration in which we run the experiments, but also in terms of the physics that is being represented. Again, in the simplest configuration, we have a very idealized treatment of radiation. And for instance, we do not have clouds. Some of you, or maybe most of you, might know that clouds remain some of the largest source of uncertainties in our future projections. And so here we really are trying to take them away and see what is it that we can robustly say in terms of circulation and precipitation changes in the absence of these processes that remain, again, poorly understood and poorly constrained. And then again, there is a lot, and I'll just show you one example that I think we have learned, and we can learn from this more idealized models, but then of course there is a large gap between the comprehensive Earth system models and these very idealized models. So how do you fill the gap? You can try to do it by, for instance, moving along one dimension in this parameter space, for instance, by keeping the idealized aquaplanet configuration and putting in back, in terms of the represented physics, things that we took away, again, in the simplest, in the most idealized configuration. Or we can also move along this other dimension in the sense that we can retain the idealized physics, but then start making the lower boundary more realistic, that is putting back in their continents, topography, ocean circulations. And I really, again, like to use really all of the full model hierarchy that I try to schematically represent here. So what is it that we have learned? Again, I think there is a lot that we have learned, but I'll focus on just one specific example. Going back to monsoons, if you open up any textbook, monsoons are described as large-scale, continental-scale sea breeze circulations driven by the contrast in thermal properties between the land and the ocean, with the land during the summer warming up much more rapidly than the ocean, which drives temperature and pressure gradients, driving a circulation that again supports the inflow of moisture air into the continent, supporting precipitation there. So this view really emphasizes the importance of the land-sea contrast in driving these circulations. And yet, and this dates back to a few years ago already, we actually showed that we can simulate monsoons even over an aquaplanet. We have to be careful about how deep or shallow we make the ocean that covers our surface of our planet. And again, I'll tell you what that is. So first of all, let me show you that at least there is some capability in this idealized simulations in representing some monsoon-like transitions in precipitation. And let me start by showing you in the upper plot, this is based on observations for the Indian monsoon. And this is one way in which we can look at the seasonal cycle of precipitation, again, from observations in the Indian monsoon sector. This is an molar latitude versus time. This shows you how the latitude of the rainfall band, this is averaged in longitude over, again, the monsoon sector, how the latitude of the peak in rainfall changes through the season. And so you see that at the beginning of the warm season, really there is a major reorganization of the tropical precipitation pattern over the Indian sector, from precipitation maximizing near the equator over the ocean to jumping at subtropical latitudes, primarily over the continent. So these two show simulations with my Aquaplanet model, one in which the lower boundary is a very shallow mixed layer ocean. Here we're talking about only 0.5 meter of water, whereas this one is a much deeper mixed layer, 50 meters, which is much more in agreement with mixed layer oceans that we observe. So you have to think about this as this hypothetical surface that has very low heat capacity, very much like a land surface over our planet, but not limited in moisture. This is a swamp. And so here, I want to argue that it's only when you have a shallow mixed layer, even without any Lincei contrast, that you can simulate monsoon-like transitions in the tropical precipitation patterns, in that, again, precipitation is primarily organized along subtropical convergence zone that shift rapidly from one summer hemisphere to the opposite summer hemisphere. Whereas when, again, the mixed layer ocean is much deeper, you see that the precipitation remains close to the equator. There is no rapid monsoon onset, such as the one that you see in the observations. It's a little bit hard, I know, to visualize the results from the Aquaplanet simulation, so let me show you these results in a little bit of a different way. Again, these are the observations for the month of July. Shading is, again, precipitation. And this is a snapshot of our Aquaplanet model with the shallow mixed layer depth. And again, shading precipitation, and the gray vectors represent the low-level circulation. And I hope that you can see, and again, this is a snapshot over northern hemisphere summer. I hope that you can see that even without any Lincei contrast, even without any land masses sitting north of the equator, this model can reproduce a shift of the major convergence zone at subtropical latitudes, very similar to what we see over the Southeast Asian monsoon sector, with similar lower level wind patterns. And so this suggests that the fact that we can simulate monsoons even on an aquaplanet, but only over shallow oceans, suggests that land is a driver of monsoons, not in that it establishes the land-sea thermal contrast and near temperature gradients, but because it provides a surface with low enough thermal inertia that allows the convergence zone to migrate, and to do it rapidly into subtropical latitudes. Recent work by Guin has looked in more details at the rapidity of this transition of the convergence zone into subtropical latitudes. This is, again, based just on aquaplanets with different mixed layer depth. This is the ITCZ migration rate versus the ITCZ latitude, and this shows that the ITCZ migrates the fastest after it reaches a critical latitude of about 7 degrees north. This means that if, thanks to the lower boundary, you can push the ITCZ further poleward than 7 degrees, then the ITCZ will not be able to remain any more close to the equator. It will jump very rapidly at higher latitudes into the subtropics. And so so putting together a lot of work, this is a schematics that we have proposed in a recent review paper in 2020 that, again, allow us to differentiate these two different regimes, a near equatorial tropical precipitation regime and a monsoon regime, and the circulations in which they are embedded. In these two regimes, the circulations are driven by different drivers, are governed by different dynamics. And we have at least some aspects of theories that will tell us how these two different regimes should respond to perturbations. So this really provides a guiding framework to interpret observations, but also simulations for both for present-day climate and future projections that hopefully will tell us more robustly how we expect monsoons to change with climate change. So I'm going to put up my summary slide. I will let you read it. And again, I really want to emphasize how important I think it is to that not only our modeling capabilities, but also our theoretical understanding go together and work together. And I'll stop here. Thank you.
Yes, thank you very much. The talk is open to discussion. Are there questions? Yes.
Io traduco, sì.
Allora, la cosa molto interessante è l'asimmetria che c'è nelle precipitazioni. Questa asimmetria sicuramente è determinata dalla maggiore pressione della Hadley Cell che ovviamente si è espansa. Ora, i motivi per cui si è espansa possono essere determinati da diversi fattori. Tu dicevi che il fattore fondamentale, che sembra spiegarlo, sia il fatto che c'è più terraferma, diciamo, c'è meno... Ho capito male? No.
Non è quella,
Okay,
è l'oceano che,
esatto.
che trasporta energia dall'emisfero sud all'emisfero nord.
Sì.
Non è che c'è più terraferma, anzi in realtà il fatto che c'è più terraferma darebbe uno spostamento dell'ITCZ nell'emisfero opposto. Yes, sorry, well, I'm still clarifying the question. And then I will try to translate everything,
Okay,
if you guys don't mind.
Yes. Per quali motivi secondo te quindi avviene questo allargamento del radiocell e quanto rientra in questo il problema dello sghiacciamento del polo, quindi quanto rientra in questo il quantitativo di umidità rilasciata, quindi la temperatura superficiale del mare, quanto rientra in questo quello che noi produciamo nella parte più a nord dell'emisfero, quindi con tutta la produzione di calore data dall'attività umana. E più o meno queste, poi non ce ne sarebbero tante altre.
Posso rispondere in inglese? Okay, so I think the question here I got a little bit confused about, but I think from what I understand, the question, I mean, maybe there is two separate questions there. One was what creates this asymmetry. Can I have the slides back? Oh, easy. I think that one of the questions was what creates this asymmetry between the southern and the northern cell, right? So what is pushing the ITCZ north of the equator? As I mentioned, and this is again something that has really come together with a lot of advances in what controls the ITCZ position. Again, it's not based, as one might have guessed, by the fact that the northern hemisphere is warmed by the presence of more land masses than in the southern hemisphere. In fact, everything else being equal, just because the land surfaces, especially in desert regions, can cool off very efficiently through infrared radiation. If nothing else, the presence of more land masses on the annual average would drive a southward shifted ITCZ. So it's really the ocean that is transporting energy from the northern to the southern, from the southern to the northern hemisphere. And the Hadley cell needs to accomplish an oppositely signed transport across the equator. And it turns out that the Hadley cell in general, not always, but in general, is thermally direct. That is, it transports energy in the direction of the upper level flow. And so to have a Hadley cell that transports energy from the northern to the southern hemisphere to compensate for the ocean energy transport, you need to have an ITCZ that is sitting north of the equator, so that again, through its upper level branch, primarily, the Hadley cell is transferring energy in the opposite hemisphere. Then the question is, how does the Hadley cell respond to any perturbations that we might generate through anthropogenic activities? I think that one specific question was, for instance, related to the what happens in the higher latitudes, for instance, in the Arctic region. And I would say that, again, a lot of the advances in the understanding of what controls the ITCZ has really come from the evidence, from paleo records, from simulations of different complexity, that the Hadley cell really cares a lot about what happens in the higher latitudes. And we have interpreted the response of the Hadley cell through, again, changes in the large-scale energy budget. And so, for instance, if you perturb the high latitudes by, for instance, putting a warm anomaly in the, let's say, the Arctic region, then you're requiring less energy transport by atmospheric circulations that in the higher latitudes is done by the extratropics. That warm anomaly through this, it's transported by large-scale extratropical storms. So that because, again, these extratropical storms propagate the signal, the warming signal, to the lower latitudes, and then it's the job of the Hadley circulation to compensate for that. And so if, again, this was the only thing that mattered, we would expect an expansion of the ICC, even further shift of the ITCZ into the northern hemisphere. We haven't seen much evidence of this poleward shift of the ITCZ in climate models because there are many other things that change. We have seen a narrowing of the ITCZ. This is to say that, again, as always, it's guiding theoretical frameworks that really allow us to try to understand how, again, something as fundamental as the Hadley circulation respond to climate changes. Does that answer your question?
Okay, so there are no remote questions. Are there any more questions from the floor? Yes.
Very nice talk, Simona. I'm going to do this because it muffles my voice. But experience with higher frequency disturbances in the tropics, like the Madden-Julian oscillation, equatorial waves, has shown that the effect of high clouds on radiation is a zero-order effect. It's really driving these circulations, as it were. And the failure of the same climate models to produce this kind of phenomenon makes one suspicious that it's because they're not dealing very well with convectively produced high clouds. So my question to you is, do you think the same flaw, known flaw in climate models might be responsible for some of these much longer time scale biases you've been talking about?
So I think that you are absolutely right, and I think that at least when it comes to looking in more details at the impact of some well-known biases in the representation of convection in climate models on the specific simulation of monsoons, more than the ITCZ hasn't even started. And I think that there is a lot to be learned in experiments where, again, even if nothing else, you try to look at, for instance, cloud locking or other locking experiments where, again, you can try to disentangle in a quantitative way the specific impact that certain effects, as well or badly represent that they might be in climate models, is on monsoons. So I think that there is a lot of work that is being done. I think some has begun on the ITCZ and the Hadley cell in terms of the zonal average, but in terms of, again, the seasonal and regional manifestations, I think there is still a lot that we need to learn.
Thank you.
Okay. Thank you very much. We might have time for a very, very brief question and answer, if there is one.
Forgive me for a very naive question from a biologist. So you put a lot of emphasis on the energy balance. So and now my question is, what's the effect of the albedo, so the color of the surface on the overall budget of energy, and in particular, where does the water for all this rain come from? From the soil, from the land, or from the sea?
Yeah, so this is a great question. There is a lot in there, and I'll try to answer somewhat briefly. So especially at the beginning, because the continents are emerging from very dry winters, especially at the beginning of the season, most of the moisture comes from the nearby oceans through convergence of atmospheric motions. And then, of course, you start getting more local recycling, but there is very little at the beginning because, again, the soil is very dry. But once it starts raining, especially in certain monsoon regions, you see very rapid vegetation changes, and then can have the very important quantitative feedback on the circulation through, again, among other things, changes in albedo. These, I would say, vegetation feedbacks are not well captured right now in climate models. So for instance, in the mid-Holocene, let's say 9,000 years ago, there is paleo evidence that the Sahara was much greener and much wetter than it is now. And when we run climate models with mid-Holocene conditions, they have a very hard time at reproducing the expansion of the rain belts as far northward as would be consistent with paleo evidence. And I think that, again, there is a lot of work that is being done there, but I think that the evidence, there is consensus that a lot of it is missing vegetation feedbacks in climate models, and probably the coupling with clouds. So again, this is a great, I don't know how to say it, but there is a lot of active research that is being done right now on that.
Okay. We have time. Well, let's thank all the speakers again for a very interesting session, and I would also like to thank Andrea Rinaldo, who kept the online part going there.